here and we convert them into a Z domain. That's a very simple statement, but it representing a trick, a very, very powerful trick that an engineer, or specifically a signal processor, people doing signal processing need to master is the following. You have several domains. The transform is really mapping something from one domain to the other domain. Okay, and a lot of the time when you're dealing with something in one domain, if you find it very difficult, map them to another domain, and maybe it is simpler to analyze in the other domain. So it's really like someone with very different perspective of the world, right? And the Fourier transform we learned on the first day and the second day, you see it providing us like that. A lot of the time, things very difficult in time, you go to frequency. Sometimes difficult in frequency, we go to time, right? So you really need very flexible, right? Try to look at the thing from different angle and maybe find a simple way of looking at the thing. Okay, so that's the key message. That's really like the trick, typical code, allowing us to analyze, design a system very effectively. Okay, so I'm using my trick now is looking at this system, and now let's see what happened in the Z domain. So the Z domain, what is Z transform of this? Y Z, right? Not too difficult. So Y Z, and because the Z transform is linear, so everything can become linear, so it becomes A1. And what is Z transform of this?
Z power minus 1.
Z minus 1 Y Z. It's not hard to see, isn't it? Right? Because if I take a signal and delay by n minus 1, I just replace n minus 1 here, and then suddenly there's Z minus 1 pop out. Okay? Very simple to show. And if I delay, so you see that why the Z transform is powerful, because it deals very nicely with the delay. Delay just pop out a Z minus 1. Okay? Any delay operation becomes Z minus 1. So I delay by 1, delay by n, just multiply them, so plus Z to the minus n Y Z. And this guy similarly. So B0 XZ plus BM Z minus M XZ. And I can mash out this thing together, and I can write Y of Z over Y of Z simply equal to something multiplied with XZ, and that is just 1 minus summation of A K Z minus K, okay, from 1 to N, and then summation on B L 0 minus L, and L from 0 to N. Okay. So you see now the input and the output relationship of this simple difference equation can be represented now in this very simple form. And this particular guy here, just simply taking the input in the Z domain, multiply with something. And this thing, by the way, is a constant. Now this thing is something is fixed, right? It doesn't depend on the input, right? This thing doesn't depend on the input. This thing is really representing, capturing these equations. And like the convolution equations, so when I write this thing here, a very simple thing is, maybe I can put it as a theorem here. I let it to prove right away a simple, it is if x, y equal to x convolution with h, in the time domain, then simply in the Z domain, y of z equal to x of z times x of z. It's like the thing in the frequency domain, right? Everyone, well, who's seen that theorem before? Okay, one thing. If not, you can try to prove it again, at home. So, by doing that, what I having here is this particular thing now is simply a filter AC. And you can see that my simple filter like this simple filter like this here, actually implementing something realizable because I can use the difference equation. And it allows me to compute a filtering operation with an infinite impulse signal, right? This thing I cannot compute by the convolution operation, but I can do them using the difference equation. And this difference equation giving me this form. So is that quite clear? All right. Okay. So we have that. So now let's try to understand this transform. A little bit more. So maybe my summary statement is okay. These two things are really directly connected. So here is maybe I put big words here. This is a for implementation. This is for implementation. I use this form, and this is for design and analysis. Right? You see, so early on we talked about we had to design a system. Design a system, or the system is given to us and we have to analyze. Right? For example, we have a biological system that we model like a linear time invariant system. So we have to analyze it. So we use the Z transform, we use the Fourier transform, and so on to design them. And then to analyze them. And maybe after analyze them, maybe we design a similar system. So we design something, and then when we design them, we have to restrict ourselves to this form. And I can tell you that every time you have a system having this form, then you can give to a programmer to program it. Right? It is a following concept. So let me write here. Stability. You design systems, and you need to guarantee the system is stable. Stable in our single sense is called bounded input bounded output, or BIBO, right? So the BIBO stable, and BIBO stable here saying the following thing. I have this system, linear time invariant systems, right? So now let me go to the system S, but I go to the system by H, the unit pole is formed. And it have input and it have output. So as a designer, the only thing you can control is a controller system. Right? You design a system, let's say you design a